Now, in earlier model, we have learnt about great orthogonality theorem. In this model, after studying this model, you shall be able to know the importance of direct product representation, learn the relation between direct product and irreducible representations, learn few informations about the direct products of irreducible representation, take the direct products of irreducible representation and reduce wherever it is possible. Now, till now we have seen the great orthogonality theorems, rules derived from this and the application. In this model, we will deal with the direct product representation. This direct product representation is very helpful in dealing with the application of group theory in quantum chemistry, particularly in connection with selection rules in spectroscopy, that is IR, Raman, etc. The direct product can be taken between any number of irreducible representation, whether or not these are associated with any linear vectors. In many cases, it is even not necessary to know their basis of representation. If a matrix A is of n into n dimension and B is a matrix of m into m dimension, then the direct product is defined as nm into nm dimension matrix, which is written as A direct product B is equal to C. Symbol over here, that is the symbol circle, we have a cross sign, is a standard notation for direct product. It does not mean the symbol of plus or product. It means a direct product symbol taken in a particular manner. Let us take two matrices.
Let us try to understand the direct product between two matrices, let us say A and B, and let it be equal to C. Notice that here this particular symbol is a standard notation for the direct product, and it is not a sign of simple multiplication, which in turn is represented by this symbol. So you can notice the difference between these two symbols, that is, this is the direct product and this is the simple sign of multiplication. Now let us try to understand this with, let us say the matrix A is having these two columns and two rows, and these are the elements. Similarly, let us say that the matrix B is represented by this, and these are the elements, that is B11, B12, B21 and B22. So this is also a 2 by 2 matrix. Now, if we have to find out the direct product between A and B, what we will do is, that is, we can say that A with, this is the symbol for direct product, with B will be given by, we can rewrite, that is, it will be this multiplied by this. And let us try to understand how this will be done. So we have these two matrices, multiple being directly, and the direct product of these two will be, we take this matrix and we say that it is being multiplied by this, and this is being represented in terms of this. So what we have to do, we have to take each element of A and multiply it with B. So this can be written as that A11 multiplied by B. Similarly, you can have A12 multiplied by B, A21 multiplied by B and A22 multiplied by B. So we take this earlier expression and we expand this. That is, the direct product of A and B will be, it is A11 with, in place of this matrix B, you will have B11, B12, B21 and B22. That is, what we have done is, with A11 we have multiplied the entire matrix B. So this comes in this position. Further, it will be, we take the next term which is A12 into matrix B, and how that will be expanded, it is A12, let us write it this way, and for B matrix, now here this will be multiplied by B11, B12, B21 and B22. Now similarly, when we take this term A21, so it will be A21, let us write it 4 times, and we have to multiply it by this entire matrix B, so we will write B11 here, B12 here, B21 and B22. And now I think it's very obvious how we'll be expanding this term, that is A22 into the matrix B. We write A22 at these places and it is being multiplied by B11, B12, B21 and B22. So what we get is, you can see this is the matrix which is the direct product of A into B, and notice that both A as well as B were 2 by 2 matrix, and what you have got is the product matrix, and what you have got as the direct product matrix of A and B is, you are having 1, 2, 3, 4 and similarly 4 here, so it is a 4 by 4 matrix. Now let us try to take an example to find out the direct product, and let us take that we are given that A is 4, 3, 2, 1, this is the 2 by 2 matrix, and another matrix given B is 3, 1, 2, 1. So now in this case, the direct product, that is A and this is the direct product symbol with B, will be given by, what we have to do is, we have to take this first element of A, that is from the first column and first row, and we write it at these 4 places. And what we'll do is, we'll take all these elements of B and write in respective places, that is, it is 4 into 3, 4 into 1, it is coming from this position, then 2 will come here and this one will come here. Now let us take this element which is 3 for the matrix A, so we write 3 here, we write 3 here, here and here, and now this is being multiplied by all these 4 one by one, that is 3 multiplied by 3, 3 multiplied by 1, 3 multiplied by 2 and 3 multiplied by 1. Similarly, we now take this particular element of the matrix A, it is 2, and we write 2 at these 4 places, and what we'll do is, we'll multiply by 3, then 1, then 2 and then 1 in these respective places. That is, what we get is 2 multiplied by 3, 2 multiplied by 1, 2 multiplied by 2 and 2 multiplied by 1. Now similarly, taking this element, which is the second row and second column element for matrix A, we will write this here, here, here and here. And we will take these four elements of matrix B and multiply them here. That is 1 multiplied by 3, 1 multiplied by 1, 1 multiplied by 2 and 1 multiplied by 1. And this is the 4 by 4 matrix that we have obtained. That is, you can clearly solve it further. So what we get, you can clearly see, is now 4 into 3, you get 12 here. 4 into 1, you get 4 here. 9 here. 3 in place of this. Then 8, 4, 6, 3, 6, 2, 3, 1, 4, 2, 2 and 1. So what you can see is this is the direct product between the matrix A and B that we had taken, which were 2 by 2 matrix each, and the product is a 4 by 4 matrix.
Direct product between two or more irreducible representations can be written as tau alpha beta gamma is equal to tau alpha, direct product tau beta, direct product tau gamma. This symbol, again, as I am telling you, cross sign in circle is not a addition or multiple sign. It is the way how a direct product is taken. The character of the direct product representation for any operation R is given as chi tau alpha beta gamma for operation R is equal to chi tau alpha R, direct product chi tau beta R, direct product chi tau gamma R. The basis for direct product reducible representation is all possible products of basis for individual irreducible representation. To generate direct product representation, we simply multiply together the characters of component irreducible representations. Symmetry operation by symmetry operation. The resulting representation tau alpha beta gamma may or may not be reducible. In either case, the dimensions of the product, that is LP, is the product of the dimensions of all the representation. That is, LP is equal to summation pi is equal to Li. That is, we take the direct product of all the dimensions of separate reducible representation. Direct product relationship. Let us take example of C4V point group and deal with the relation one by one. In C4V, we have A1, A2, B1, B2 and A. And this is the character table in which various entries are given: E, 2C4, C2, 2 sigma V, 2 sigma T. The partial character table for CV point group is given. Now, several important points about irreducible representation and their products are given. If all irreducible representation whose direct product is taken are of one dimensional, that is non-degenerate, the product representation will be one dimensional. Take the example A1 into direct product with A2, B1 into direct product B2, direct products in C4V point group, and we will get the result as thus direct product of A1 into A2 gives the character as 1, 1, 1, minus 1 and minus 1. These characters correspond to A2 irreducible representation, which is also of one dimensional in nature. Now take the direct product of B1 and B2 irreducible representation in C4B point group. This direct product of B1 into B2 gives me character as 1, 1, 1, minus 1 and minus 1. These characters correspond to A2 irreducible representation, which is also of one dimensional in nature. Product of the form A into A, B into B, A into B for all groups are defined as A1 into A is A1, A2 into A2 is A1, A1 into A2 is A2. This product I mean to say direct product. B1 into B1 is A1, B2 into B2 is A1, B1 into B2 is A2. Except for the B representation for D2 and D2H, where B1 B2 is equal to B3, B2 B3 is equal to B1, B3 B1 is equal to B. That is, in point groups where we are having more B type of irreducible representation. Here it is D2 and D2H, which I have taken over here. The product of a non-degenerate irreducible representation of the type A1, A2, B1, B2, etc. with a degenerate irreducible representation of the type ENT. It is a degenerate representation. This direct product may be the same representation or another representation. Let us take the case of B2 and E direct product in C4 point V over here. This direct product of B2 into E gives me the character as 2, 0, minus 2, 0, 0. These characters correspond to E irreducible representation, which is two-dimensional in nature. In this case, it is the same degenerate representation as there is no other degenerate representation in the point group. Now, let us take the product of the form A into E, that is A direct product of E, B direct product of E. First of all, for all groups, A into E is E, irrespective of the suffix on A. For all groups except D and D, etc., S8, B into E1 is equal to E, B into E2 is E1, irrespective of the suffix on B. If the group has only E representation, then the direct product will be E. The direct product of any representation with a totally symmetrical representation will be result in same representation. That is, we take C for V. A1 into E is E, B2 into E is E. That is, here I am taking the direct product of one-dimensional representation and two-dimensional representation. The direct product of two or more degenerate representation is a reducible representation. Let us take C for V character table and take the direct product of E and E. And by taking the direct product, we get the characters for the direct product as 4, 0, 4, 0, 0. Thus, tau for E into E can be reduced to, that is this 4, 0, 4, 0, 0, it can be reduced to A1, A2, B1, B2. Decomposition can be verified easily. Take the sum of the characters of irreducible representations A1, A2, B1, B2, it will be equal to the direct product, that is E into E, that is 4, 0, 4, 0, 0. Now, the direct product of representation of an irreducible representation, say one dimension, with itself is or will contain the totally symmetric representation. That is, we can take the direct product of A1, A1, A2, A2, B1, B2, we will get the result as A1, as shown in this table over here. We get the corrector for A1. Now, the direct product of irreducible representation with itself will contain a totally symmetrical representation in it, and the totally symmetric irreducible representation will appear only one. That is, if we have the two-dimensional representation and take their direct product, we will find it is a reducible, and reducible representation will have a totally symmetrical representation in it, and that will repeat only once. That is, if I take E1 into E1 and reduce it, we will get the result as A1 plus A2 plus E2. E2 into E3, we will get A1 plus A2 plus E1. E into E, we will get A1 plus A2 B1 plus B2. Similarly, if we take three-dimensional representation, T1 into T1 is A1 plus E plus T1 plus T2. T2 into T2 is equal to A1 plus E plus T1 plus T2, and so on. That is, we can get the direct product and reduce them. Now, in general, for symmetry and anti-symmetric, with respect to a symmetry operation in representations we have, that is, if we have a representation and which is, I say, symmetry, then if we take the product symmetry into symmetric, we will get the symmetric direct product. If we take the direct product of symmetric and anti-symmetric, we will get the anti-symmetric representation. If we get the anti-symmetric and anti-symmetric, we will get symmetric structures. In terms of Mulliken symbol, we can represent these as, if it is of G type, G into G is G, J into U is U, U into U is J. That is, if we have one-dimensional representation, A1G, AG plus AG, I will get AG, AU into AU, I will get AG, AU into AG, I will get AU, and so on. Similar is, we are having prime and single prime, prime into prime, that is single prime into single prime equals to single prime, as shown. Then we have single prime into double prime, we will get the result as double prime. Double prime into double prime, we will get single prime, that is double prime multiplied or direct product, we will get single prime. Like this, A1 dash into A1 dash is A1 dash, A2 double dash is A1 dash, A1 dash into A2 double dash is A2 double dash. That is, in this module, I have given the importance of direct product representation. Why this direct product is important? It is very, very important in quantum chemistry, and it is also very important in dealing with the IR spectroscopy. And you will see later on that when we want to find out the reactivity of a particularly vibrational mode, we have to every now and then have to take the direct product and try to reduce it, and then we have to find out the activity. Relationships between direct product and irreducible representation were cited and explained with the help of few examples. More information about the direct products of irreducible representation were provided. Taken the direct product of irreducible representation and reduced wherever possible. Thus, in this module, we have seen the importance of direct product, what is the meaning of the direct product, and that has been explained by taking the two matrices A and B, and we have seen if we take a matrix of n into n dimension and another matrix of B m into m dimension, then the direct product matrix will be n into m dimension into n into m dimension, that is total dimension will be nm type like this. So, in this module we have learnt little bit about direct product, and you will find in later on that this direct product representation is very important. If you understand in this, then it will be easier for you later on in dealing with the IR spectroscopy.